For number 1, we are going to check if the given system exists and whether it has unique solution. So to do this, we will conduct 2 simple tests. So for test number 1, we will simply substitute the given initial value y of 0 equals 0 to the given function 3y raised to 2/3. Okay, so we get here 0. So this means that it is continuous so therefore it exists. So that's for the first test. For the second test, we will simply derive the function with respect to y and then substitute the given initial value. So we get here simplify and our final answer is 2 over 0, which is not good. It is undefined. So it tells that it is not continuous. And therefore, no unique solution. So that's our answer for number 1. Now we move on to number 2. So for number 2, determine the maximal intervals on which the solutions to d IDP dy over dt equals 1 plus ln of t and y of 1 is equal to 1 exist. So let me first write the general form. So the numerator should be y plus p of t y equals f of t. So from the given, what is our p of t? So we don't have a term with y, so it means it is 0, which is good. It tells that it is continuous. 0 for all x, value of x. Or we can say that the interval is negative infinity to positive infinity. So what is the value of our f of t? So we have 1 plus ln of t. If we will analyze this, the value of t can only have 0 to positive infinity, but excluding 0, because ln can only take values greater than 0 positive. Okay, so for any negative number including 0 is not possible. So next, what is the intersection of these two intervals? So we can easily say that it is 0 to positive infinity. Then, what is the so the question is, this given y of 1 is equal to 1, is it in this interval? So the answer is yes. So our final answer would be this interval. So this is our maximal interval. Now we move on to number 3. So for number 3, we should we should transform or put the given into linear state space form, which is this. So given for number 3, linearized systems, we have here dx over dt equals 3x squared, wherein our x naught is equal to 2. So we transform this to this form. Our f of x is now is approximately equal to f of x naught plus the derivative of the function with respect to x, such that x is equal to x of x naught multiplied by x minus x naught. So we substitute three times 2 squared plus the derivative of the function 6, and then the value of x is the value of x naught, which is 2, multiplied by x minus x naught. We simplify this and we get 12 plus 12x minus 24, or 12x minus 12. So that's our final answer for number 3. For number 4, it has y naught. So the only difference compared to number 3 is that we should add something for y naught. So it will become a bit longer than number 3. So our linear state form here is, space state form here is f of x is equal to f of approximately equal to f of x naught y naught plus derivative of the function with respect to x, such that x is equal to x naught and y is equal to y naught multiplied by x minus x naught plus derivative of the function with respect to y, such that x is equal to x naught and y is equal to y naught multiplied by y minus y naught. Okay, so we just follow this form. We have dx over dt equals, so we substitute the value of x with y naught, with x naught. So we get here 2 minus 2 squared plus derivative of the function with respect to x, 3 times x minus 2 plus the derivative of the function with respect to y. So we have negative 2 y times y minus 2. So we simplify this. 6 minus 4 plus 3x minus 6 minus 4y plus 8. So our answer is 3x minus 4y plus 4. So this is our final answer for number 4. Now we move on to number 5. So the question for number 5 is, okay, so we have given here, consider the vector of x prime is equal to the matrix A times vector x, where this is the matrix A. So for item A, find the general solution. B, solve the initial value problem given that the vector x of 0 is this matrix. Sketch the phase portrait and then determine if it is stable or unstable. Okay, so we write here the matrix A. So in matrix A, we have to compute for the eigen values and eigenvectors. So I computed it earlier. So we should get the same value of lambda 1 equals 15 and lambda 2 equals 6. And we have eigenvectors of 5, 1, 1, 2. Okay, so from this we can find the general solution. The vector of x prime equals C1 e raised to lambda 1 t with this matrix plus C2 e lambda 2 t and this matrix. Okay, so we substitute the value that we get, the eigenvalues and the eigenvectors. So we have C1 e raised to 15t plus C2 e raised to 60 1, 2. So this is our general solution. To solve for the initial value problem, so we simply solve for C1 and C2. Okay, so from matrix A, we will use this eigenvectors to compute for C. Okay, this should be zero. Okay, so now to get the C1 and C2, we have to inverse this and then the determinant. So the determinant is 9, 2, 3. So we compute for C1, it should be 2 times 2 minus 1 times 3 over 9. So that's for C1. And then for C2 is negative 1 times 2 plus 5 times 3 over 9. So what will be our answer? This is 4 minus 3, so 1 over 9. So negative 2 plus 15, that is 13 over 9. So now we get the value of C1 and C2. We substitute it on the general solution. 1 over 9 e raised to 15t 5 1 plus 13 over 9 e raised to 60 1 2. So this is our answer for letter B. So to determine if it is stable or unstable, we simply check the sign of the eigenvalues. So our eigenvalues are both greater than 0. So this means that it is unstable. So that's all for number 5. And then on our next video, we will answer other sets of problems. Thank you.